So we've now seen how we can get these spatial maps from the output of the last convolutional layer when the image is passed in. These spatial maps are typically much smaller in size than the input, typically between 7 by 7 and 14 by 14, varying according to the choice of architecture and the size of our input. The third dimension here is the number of spatial maps that are output by the last layer, which differ based on the architecture, so we just use K here. Let's now see how we can go from these K spatial maps of size 10 by 10 to a heat map over the whole image. Let's unpack these spatial maps. So we can represent each square here as a spatial map going from capital A1, capital A2, to capital AK to denote the K spatial maps. And now what we're going to do is we're going to weight each of these maps with a weight given by small a, and then add all those up to get a localization map, L, for cardiomegaly. We can write this down mathematically with L, the localization map, as the sum over K of the weight, small k, times the map, capital AK. Small ak here tells us the influence of each spatial map on the localization map. The next question for us is how we compute these weights, small ak. We need to first understand influence. Let's say we wanted to know the influence of each feature within the A1 spatial map on the output. A1 has 49 features, 7 rows, 7 columns, and we'll use Z to represent the number of features, the number of elements in A1. Let Y represent the output score of the network for cardiomegaly right before the sigmoid activation. We can now compute the influence of each of these features in the spatial map on Y by computing the partial derivative of Y with respect to each feature in A1. And this gives us the influence of each feature on the output. This gives us a matrix telling us the influence of each feature on the output. Here the feature at position 2, 2 is having the greatest positive influence on the output because this number is the highest of all numbers, at least the ones we can see here. The feature at position 1, 2 is having the greatest negative influence on the output of these 4 example values. We can get the average influence of the spatial map A1 on the output by taking the average of the feature influences at each of these positions. Formally, we do this by taking the sum over I and j, so this is over the rows and columns, of the individual values at each of these positions, and then to take their average, we do 1 divided by the number of elements in A1, and this way we get the average influence of A1 on the output. The average influence can then be used as the weight we're seeking for the spatial map, small a of k, in computing the localization map. We thus now have the full expression for the computation of the localization map, along with where small a of k comes from.